Let's talk about a different kind of confidence interval. So this time we are going to have sigma not known. Sigma, as you know, is our population standard deviation. So, think about it. If you knew population standard deviation, you probably know the mean and you know the truth. So this is more usable. So we're going to do a confidence interval when we don't know sigma. So we're going to change it up and we're going to use not a z distribution, which is a standard normal distribution, which we've been used to using. We're going to use something called a t distribution. Now there's a family of t distributions and it's based on the sample size. So it kind of looks like a normal distribution, but it's a little bit flatter. So for example, if my sample size was size, we'll say 15, it's still going to be mounded like this, but it's going to be flatter, still has an area of 1, it's just more spread out on the ends. Okay, so it's flat and more spread out. And think about it, when you have samples that are smaller, like size 15, your x bars, your sample means, are going to be a little more spread out because there's a little more uncertainty. When you have samples that are bigger, everything's going to be toward the center and closer to the truth. So we're going to say, for example, this is when n is 15. Sample size is 15. Now, if we had a sample size of 4, for example, it's going to be even more flatter and more spread out. So I'm going to exaggerate this and say this is what 4 looks like, although it really isn't, but we'll say that's what 4 looks like. So a t distribution is a family of distributions. And it was created, I can't say discovered, it wasn't always there. It was created or developed by a guy named William Gossett who worked for Guinness Brewery. And he would do research and development. And when he did this, he was using samples of small sizes. And he found out that when my samples were small, my distribution was still symmetric and mounded and centered, but it was more spread out. And when my samples got to be about size 30, it started looking normal, like our red distribution. So when we do confidence intervals, when sigma is unknown, we're going to use a t distribution. So we have this strange word, or strange 2 words, it's 3 words, degrees of freedom. So we base these on degrees of freedom. I have no idea where they got this name, but we have it. And for this t distribution, our degrees of freedom are n minus 1, sample size minus 1. So if my sample is size 4, its degree of freedom is 3. If my sample is size 31, my degree of freedom equals 30. And each one of those degrees of freedom has its own t distribution shape. The closer it is to 30, the more normally distributed it looks. The smaller it gets, the flatter it looks. So flatter like this, a little more flat. Okay? So we're going to base it on that. So I gave you a chart in your notes. It's the very last page. And that chart on the very top has confidence level. And on the side, the very left-hand side, it has the degree of freedom that matches it. So we want to look at those. Pardon my reach. All right, we're looking at this table. Let's see if we can zoom that in for you. All right, so it's called table F, this one right here. And along the top we have confidence levels, 90%, 95%, 99%. And then look over here, degree of freedom. So if my sample size was 11, the degree of freedom for a 90% confidence interval, see, sample size 11 means degree of freedom of 10. And if I scroll over for a 90% confidence interval, my t critical value will be 1.812. So hopefully you can follow along and use this chart, which you can use when it comes test time. Okay? So we will do some examples with that in our next video, but let's talk about our formula we're going to use for a t confidence interval. So I still have my x bar plus or minus a t critical value times s over radical n. So now we have sample standard deviation. So 2 things have changed. What's changed this time? We now have a t critical value, so this has changed. And instead of sigma, we have s, sample standard deviation. So our next video will practice one of those.